believe, going to do some of the presentation as well. And we have a very interesting illustration of the solar system and over here and some other artifacts. So I would invite everyone to have a look and to see what's there. But as I say, we're delighted to welcome Dino tonight, and thank you for giving up your time and your evening. And I believe some people have already been outside with Jim and have seen using his
6-inch.
6-inch
6-inch telescope.
Yeah, telescope to view the night sky. So that was quite an added extra that we hadn't expected. So I'm sure some of you, already had the opportunity to see that. So
We'll be out there after the event too, to give you, people who haven't had a chance can look through the telescope as the library is being closed down. Yeah.
Okay, that's wonderful. So if everybody is ready, let's have Dino start. And thank you very much again, Dino.
Welcome all. Tonight we're here to talk about the James Webb Space Telescope. So we'll be looking back to the beginning of time. We'll explain that a little more as we get into it. I'm Dino Tata, a Solar System Ambassador for NASA. My sidekick here is Jim Zabrowski. He's a Solar System Ambassador for NASA as well as being a physicist. And he's my go-to expert. So, anyway, it's named the James Webb Telescope. So who is he? Well, he ran NASA from 1961 to 68. And unfortunately, he passed on just before Apollo 11 landed on the moon. So obviously, he had a lot to do with it. Now, he wasn't really an astronomer. He was a businessman, and he did a great job on it. He was part of 75 space science missions designed to explore space and other worlds. And he was hired by JFK. And so many of you young people didn't know who JFK is. Keep forgetting how old I'm getting. He had 35,000 employees and almost 500,000 contractors under his direction during his tenure. So there are many types of telescopes. First of all, the opticals. Those are what you use to view planets and things of that nature. That's what Jim has set up out back tonight. So if you look through it, you were looking through an optical. X-ray telescopes, they track heat signatures. They can see through space and dust, and as we say, they go where no telescope has ever gone before. Radio telescopes detect radio frequencies from distant objects. Most objects have a frequency of some sort. Gamma ray telescopes detect the flashes that jet gamma ray emits. And space telescopes, the newest type, they operate away from Earth's atmosphere, Earth's light, and Earth's pollution, so they can get much better result than an earthbound telescope. So who invented the telescope? A couple of test questions. Was it Galileo Galilei, Hans Lippershey, Christopher Columbus, or Peter Bolaraki? Anyone want to take a guess as to who invented it?
Galileo.
Okay, that's what I usually get, and you know what? It's wrong. This gentleman, in 1608, Hans Lippershey, he was a glass maker, made glasses in Holland. He put two pieces together on a tube, and notice you could see distant objects much closer. Now the military liked this very much because the telescope we use on rifles, so it could detect the movement of enemies and they could zero in on them. So he was the inventor of it. Now, who improved the telescope and used it to prove our solar system with a heliocentric system. Now, a heliocentric system basically means everything rotates around the sun. Prior to this, people thought we had an Earth-centric system, which means the sun and all the planets orbited around the Earth. So this was Isaac Newton, Mark Pelican, Galileo Galilei, or Jim Warnick.
I'm going to take a guess, Dino, because I haven't read much astronomy for a while. But I'm going to say Isaac Newton.
Isaac Newton, okay. Anybody else want to render a guess?
Let's stick with Galileo.
2 years after Lippershey, Galilei was the first person to turn this telescope skyward, to look at the sky. He discovered the transit of Venus, which proved that we were a heliocentric system. He discovered the 4 large moons of Jupiter, and that's what we're showing you outside tonight, because Jupiter's in view and you can see the 4 large moons. We call them the Galilean moons. There's Europa, Callisto,
Io and Ganymede.
Io and Ganymede. And Saturn. Now, See, I have a question mark by Saturn here. There's a reason for that. We give Galileo credit for discovering Saturn, but in truth, it's a naked eye object. You can see that, so millions of people saw it before him. He's the guy who put the telescope on it first. And this is what he saw. Telescopes, they were brand new in those days, so the quality was pretty poor. So you see how fuzzy it is. His image may not even been this good. So he said Saturn has 2 moons on it. And that they're joking that it looks like it has ears. But things changed. This is Galileo's picture. This is the Hubble. So that's what 400 years of research and development achieved. Both are pictures of Saturn. But now we see it like this. In fact, with the telescope out back, if Saturn was up there, you could see this picture here. Well, everything evolved in this world, doesn't it? Telescopes are no different. So they started in the 1600s with a little tube. A lot of us today have scopes like this. This is what we call a Schmidt cascade. And it basically folds the light inside. That's why the tube is so short. But that's a very popular scope today. We have things like we call it a very large array. Like this is 28 radio telescopes, all chimed in and all connected. So you have the power of 28 telescopes in one. And then, of course, we have the Hubble, which is just an amazing telescope. It's done wonderful, wonderful things. And it's still got a few years left. It's not going to stop operating just because we're launching Webb. So it's going to keep going. But now we move.
I have a question.
Yes,
Is
Bob.
NASA planning an upgrade of Hubble again?
No.
So that's done. They're not going to maintain it anymore?
No. The Hubble, most of these things, NASA puts so much redundancy into all of its projects that things typically last much longer than what they're meant for. Jim, Hubble is what, 40 years old now?
Hubble was expected to survive, if they're lucky, 10 years. It's now celebrating its 31st anniversary.
So they built it with a 10-year plan, and it's got 40 years. And that's,
We're hoping.
We're hoping, and that's the way, we launched the Voyager spacecraft. They're like 12 billion miles away from Earth, and they're still sending us a message every day. They've been up there even longer, I think.
37 years.
37 years, yeah. So, but now we move into the future with the James Webb Telescope. That's being launched this year. In fact, just about a month, it's going to send out, and it's completely unique from anything else we've ever done. It's about as tall as a 3-story building, and this is the sun shield. It's about the size of a tennis court. Now you see, I got models over here. There's a model of the Hubble. There's a model of the Webb. And the model is much smaller, but that's just because that's the size the model came in. The reverse is true. Hubble is much smaller than the Webb. And here's the size comparison. Webb's about the size of a bus. And it weighs 11 tons. That's 4.8 tons more than the Webb. Why? Because we've improved our technology over the last 30 years. The mirrors on this are much lighter than the mirrors on Hubble. And new materials, new developments. When you're traveling in space, your biggest problem is weight. It costs about $10,000 to send a pound into space. So wherever you can cut a pound, you take your watch off and leave it behind, because there's $1,000, But we're not doing it alone. These 14 countries have all been building the Webb with us. And you can see the names there. And the ESA is the European Space Agency. And additional member states are also involved in the effort. So it's a worldwide effort to put this thing up there, and the whole world will benefit from it. Well, it originated in 1996 as the Next Generation Space Telescope, and its launch is scheduled for December on an Ariane 5 rocket. Its nominal mission is 5 years, but we're hoping for another 5. How long it lasts depends on how long the fuel lasts. And we take a measure to make the fuel go further, which you'll see in a minute. It's not the replacement for the Hubble, it's the successor to the Hubble. And we say that because it's not replacing Hubble, it's a different type of telescope. It's going to look at things in a different way than Hubble does. There's 4 key goals. It's going to search for light from the first stars and galaxies that formed in the universe after the Big Bang. Now, the universe is 13.6 billion years old. This is going to go back, is it 13 billion, Jim?
13.8.
13.8. So it goes back, we're going to see things we've never seen before. It's going to study how galaxies evolve and how they form. It's going to help us understand the formation of stars and planetary systems, and to study the systems and the origins of life. So it's got a big job to do,
Yeah.
but if any scope can do it, the Webb can do it. So it'll look back 13 billion years to when the universe was just beginning. But how will it get there? Well, on a rocket, of course, but it's going to launch from Kourou, French Guiana, right here off the northeast coast of South America, on December 18th, sometime between quarter 9 and 10. Now, why at that particular location for takeoff? It's close to the equator. Whenever you launch a rocket in space, you want to be close to the equator, because the Earth rotates. I think it's about 900 miles an hour. But the equator bulges a bit. We're not a perfect sphere. There's a little bulge caused by the spin. And when you leave from that area, you pick up the speed of the Earth is added to the speed of your rocket. So it gives you like a little push off the planet. It'll fly in an Ariane rocket. About 26 minutes into the flight, it's going to separate from the rocket, trigger its solar array, and start producing electricity. From then on, it'll be on solar. It's a French product, this rocket. Flown 80 missions, is considered one of the most reliable rockets in existence. You got a project like this, you don't take chances. You want it to be done in the best possible equipment you can get, the most reliable. You don't want it falling over on the launch pad. But it'll take it about 6 months to reach its destination. It'll travel as fast as at the bottom, as initial start. It's like a bike going up a hill. When you pump hard, you go fast at the bottom to get some momentum, and then you gradually slow down as you get closer to the top. This flight will be done the exact same way. It'll be located near the Sun-Earth L2 points, which is right here, 930 to 940,000 miles from Earth, directly opposite the Sun. So here's the Sun, here's the Earth, and there's L2. And there's 5 of these L points. They're called Lagrange points. And what are they? Well, they're positions in space where the gravitational forces of a two-body system like the Sun and the Earth produce enhanced regions of attraction and repulsion. And they can be used as parking spots, and this is one of the fuel-saving measures. Where if for someplace else you might have to fire the thrusters multiple times a day to keep it in place, this you don't have to. I think the adjustment is only every few days, and it'll stay there. But why this particular? Well, we have the Earth. Here's the space station, the Hubble, 347 miles up. The moon's 238,000. This is going out 940,000 miles. Away from all the light pollution on Earth, the heat from Earth. It's an X-ray telescope, so it's going to be cold. So it's ideal for astronomy because it's close enough to communicate. I guess it's almost like real-time communication because it travels that fast. They can keep the Sun, the Earth, and the Moon behind the spacecraft, behind the solar shield, so the light and the heat is all blocked. And it provides a clear view of deep space for our telescope. Well, how's it talk to us? Well, you have your light hitting the telescope. It transmits it down to a deep space network, and I'll tell you what that is in a minute. And they send it to the Goddard Space Flight Center, where they interpret the data and let us know what's going on with it. Well, this is the Deep Space Network. It consists of 3 antennas, one in Goldstone, California, Madrid, Spain, and Canberra, Australia. This is a series of large antennas, and as you can see down here, they cover almost all the sky, so no matter where the planet is in its rotation, we can still talk to the telescope. And I've seen it a year or two ago, I heard they're trying to build some more to fill in the gaps. But, Jim, would you take a minute and explain this one for them?
Yeah, that shows basically how deep the Webb is going to probe. We're going to go right to the very edge of the universe right after the Big Bang occurred. But people think, oh, we're going to go right to the moment before the Big Bang. Not quite. It took something like 400 or 500 million years for the universe to cool down sufficiently so light can be let go, basically, and we could see the light of the first stars and the first galaxies. So that's the thing that Webb will allow us to do, and it allows us to do this because of infrared energy. That gold-covered mirror is going to gather 100% of the infrared energy falling on it, and it will take either imaging or spectroscopy to look into deep space, into the first galaxies as they're forming, and the first stars as they're forming. So it's going to be radically different from what we see in the universe today, in the current era. Scientists estimate like a big star today, 50, 60, 70 solar masses. A big star back then, 300 solar masses. So they're giant stars that lived very, very, very quickly and then exploded, seeding the early universe. So that's the importance of that basic topic. That's why you're right at that edge of seeing where we could see.
Now, light travels at 186,000 miles a second. That's about 6 or 7 trillion miles an hour. But these things down here are so far away from us that light has not yet reached us. And so our scope is reaching out to pick that up. And that's why we'll see a bunch of new things. So you can see back in time to when the universe was less than 800 million years old, or just 6% of its age today. Today it is 13.6 billion years. It began in 1996, just 6 years after Hubble. So these projects like this, they don't take 4 years, 5 years to develop. They take 10, 15, 20 years. You develop new fuels, new materials, new procedures, new resources. So this is the first time a scope has ever been made like this. So just about everything on it is new. And so that's why it takes so long, in 1996 when they first started. But Webb is the successor to Hubble, as I said, because they serve different purposes. This is the Hubble. It does ultraviolet and visible light, obviously. So what you can see is what Webb sees, not what Hubble sees. It sees what you see, and plus a little bit more in the ultraviolet. You can't see anything that the Webb is going to see, and neither can Hubble. So it's infrared. It's going to be great. The infrared penetrates clouds. The visible light doesn't. So if I'm looking at you, and there's a cloud between the two of us, I can still see you in infrared. It'll go right through that cloud, and I can see you. So you get a much better vision of the universe this way. And this is an example of what it is. This is what Hubble can see, the ultraviolet, and Hubble and visible light sees this. Infrared is that. So this and this are the same picture. This is visible light. This is infrared. This is what the Webb will see. This one, you don't even know there's a victim on the ground. This one is very clear that there's a victim on the ground. So that's one of the things that's very good about this telescope. Now the size, Webb has 6.5 times more light collecting area than Hubble. Telescopes are all about collecting light. The mirror is 21 feet across. The Hubble is only 8 feet across. And just to give you an idea, standing next to a person, we are the largest space telescope ever built. This is what it looks like in the rocket ship. It is so big, there's no rocket big enough when it's expanded like this. There's no rocket big enough to take it. So the sides fold in like this. And we take it out. When we release it from the rocket up at L2, the sides will open up again. So there's 4 main elements: the telescope, the instrument model, the sun shield, and the spacecraft bus. And this is what it looks like when it's completed. Actually, if you like, when we're done, there's a model here that you can take a look at. And it has its primary mirror, the pack of scientific instruments, the secondary mirror. This is the sunshade, that's 5 layers. And this is the bus that carries all the important stuff, a star tracker, the antenna, solar array, and a stabilization flap that sort of steers it a bit. The primary mirror consists of 18 individual hexagonal mirrors. And they're built in segments or in a structure which will fold up so it can fit into a rocket. Also, using this, it gives us the closest we can get to a round telescope. You get your convex concave effect that really makes a difference on focusing. It's made of beryllium, and it's coated with 48.25 grams of gold. That's 3 grams of gold per panel, and there's 18 panels. Now, how much is 3 grams? A nickel weighs 2.5 grams. So you get about 2 1/5 nickels worth of gold. This is 3 grams of rice. That's how much gold is on each panel. Not an awful lot, right? So you think, how can that little bit cover this? Because each of these segments is 4 feet across. Well, they don't just paint it on, of course. It's put on like as a mist. It's vaporized and put on a mist. And that settles on it. And then they cover it with a protective coating. So it's quite a procedure. I don't know if it's ever been done before, honestly. Well, why beryllium? Well, it's light and strong, keeps the shape at varying temperatures. This telescope will be operating at over 300 degrees below zero. So it keeps its shape. It comes from mines in Utah. And it goes to 11 different facilities throughout the United States for manufacture. So it's all American made. The segments deployed get aligned in space by command from Earth. Now each one of these 18 things has its own motor. So we can adjust each one individually just by sending an electronic signal out. And they think now have 3 different prescriptions. This has a prescription just like your eyeglasses. There are 3 different prescriptions that are 6 each on this thing. It'll gather more light and more detail than Hubble, and the segmented shape allows the segment to mirror the high filling pressure. And it needs to be very cold because it's an X-ray telescope. They have to be very cold. This will be operating at 370 degrees below zero. And I'm only glad I don't have to be there to hear it. The question always comes up about how do we service it? We don't. It's almost 1 million miles away. It's not like the Hubble is only 300 miles away. We have redundant systems in here that should take care of it. So the Integrated Science Module, this is the heart and soul of the Webb Telescope, and it contains the 4 main instruments that will detect the distant galaxy. MIRI, FGS, NIRCam, and NIRSpec. We'll get into what those are for you. The sun shield it's to block light and heat from the sun, the earth, and the moon. And the L2 points keeps all 3 bodies on the same side of the spacecraft at the same time. It maintains a constant environment for sun shield and solar arrays. It's made of a polyimide film, has membranes coated aluminum on one side and silicone on the other side. It's designed to be folded 12 times so it will fit into the rocket. And it was hand assembled at a company called Mantech in Alabama. It's approximately the size of a tennis court. It has 5 layers when it's deployed. You can see the size of it just by these people standing next to it here. The spacecraft bus, it provides support for necessary operations and home for 6 major subsystems: the command and data handling, the electric, the attitude, communication, propulsion, and thermal control. So you see why this is the heart and soul of the telescope. And that's the whole package put together. So what's inside it? Cameras that take pictures of astronomical objects, a spectrograph to break light into colors for analysis, and coronagraphs so we can see what's near the stars without the star blinding us. So the near-infrared camera, it's called NIRCam. That's from the University of Arizona. The NIRSpec is a spectrograph made by the European Space Agency and NASA. MIRI is by the European Space Agency and NASA. And the Fine Guidance Sensor, the FGS, that's near-infrared imager and slitless spectrograph made by the Canadian Space Agency. So you see, this really is an international effort. So the near-infrared camera, NIRCam, it'll detect the light from the earliest stars. NIRCam is equipped with a coronagraph, and it'll cover infrared wavelengths from 0.6 to 5 microns. The spectrograph was built by the European Space Agency. It'll analyze the spectrum of an object and tell us about its physical properties. The spectrum tells us what chemicals are in an object. So that's how we know what a planet is made of. It has a multi-object capability and a micro shutter system to control how much light enters it. And the near mid-infrared instrument covers wavelengths from 5 to 28 microns. Its detectors will allow us to see red-shifted lights of distant galaxies, newly formed stars, faintly visible comets. It has both a camera and a spectrograph. Now the redshift light we've learned that light reflects movement. So if an object is flying towards you, it appears blue. As it goes away from you, it appears red. So if it's red, you know it's moving away. If it's blue, you want to duck. But it does help. And the easiest way to do it, if you stand by a railroad, you hear a train coming, you hear woo, woo. The sound changes once it passes you. That's the general effect. And the 5 guidance center has a wavelength of 0.8 to 5 microns. It's a guider which helps point the telescope. Well, what about the power of this great big thing? The Hubble sees the universe when it was in its toddler stage. The Webb sees it when it's a baby. That's how much further back it goes. The Webb can see the heat signature of a bee if the bee is on the moon. That's how powerful it is. And it can see the detail of a penny from 24 miles away. So it's pretty powerful, right? Now, what we saw with Hubble is, this is the Hubble Ultra Deep Field Telescope with the ultraviolet. To make this picture, they aimed at a spot close to the Big Dipper that was completely black, not a single star in it at all. And they kept the shutter open enough so that 800 exposure equals 11 days of exposure as he orbited the Earth 400 times. This picture now shows over 10,000 galaxies. That's what we saw in a place that was empty. That's the light that hadn't reached us yet. Hubble reached out far enough to see it. And the reason you can do it, I said the other day, if you see something with your eyes don't retain it. It's there for as it passes by. With telescopes and cameras, it stays there. It just piles on, one vision after another. It keeps accumulating color and its shape and size, so you get pictures. But this only covered 1/24 millionth of the sky. Now this is interesting. See, there are only 4 stars in this picture. There's one here, and there's one here. There's one right in here, although I can't, oh, right here. Everything else you see is a galaxy. Galaxy with 100 billion stars, 200 billion stars in it. So you can imagine the vast emptiness of spaces, just more suns, stars. And every star has the opportunity to have a solar system. We found many of them in our own Milky Way galaxy. So why a new telescope if Hubble's doing such a great job? It's a different technique. It's infrared. It can look back in time further than Hubble. Its infrared capability will see through the dust and gas clouds of space. This is the Eagle Nebula. We call it the Pillars of Creation. Same picture with infrared. This is what you see with your eyes. This is what you see with infrared. All these stars, you don't see them in this picture. So that's one of the benefits of it. This is another nebula, visible light versus infrared. You see how much more you can see because infrared goes right through the star, through the dust. So, while Hubble orbits about 300 miles above the Earth, Webb will orbit about 940,000 miles away. Free from atmosphere, free from pollution, free from heat. So you're going to get some much things that you've never seen before. And it's 100 times more powerful than the Hubble. Its mirrors are over 7 times more space than the Hubble. And it's much lighter than the Hubble. Hubble weighs 2,200 pounds. Webb weighs 1,375. As I said earlier, that's because of development of new materials, lighter materials, materials that don't weigh down the spaceship as much. Finally, due to its location at L2, it will use less fuel than Hubble, make it more economical. As I said, because it's in that L2 spot, it's like a parking spot. You only have to adjust it every now and then, instead of doing it constantly. So it uses less fuel when it does that. And one final look at its size. See the man down here? I don't know if you can see him in that white outfit on the white. But that's a man compared to the telescope. And the telescope's in its closed position. Well, Webb will be very busy during its 6-month flight to L2. And with any luck at all, this video will work. And you should, this is the flight going over. Now, a couple of things to watch on this. You see the travel, you're up here and it'll move toward a spot. You see it move out. But up here, they'll show you what's actually happening at that moment. And this is the mission elapsed time up here.
Like watching a bird.
Walk through it, I tell you.
Yeah.
So there's an awful lot that has to go just right.
I'll tell you, Dino, you got me reading for the next 3 months on this thing, because, I mean, it gets heady. I mean,
How do they
Yeah.
test,
it gets heady.
You
how do
don't
they
know
test
how
the
by learning.
opening? I mean, there's so many mechanical things that could go
Well, you test them
wrong.
all on ground, and those you can test up in the atmosphere, you test in the atmosphere. But there's, the final test is a million miles away.
So when a mirror doesn't just deploy right, there's nothing they can do though, is
Yeah.
there?
Not really. It's too
Wow.
far away to serve. It's not like going to the International Space Station and fixing something.
So they're just crossing their fingers.
Yeah,
and-
well, more than crossing your fingers, you plan to do it right. You test it and you test it and you test it, and you put in a redundant system to back it up.
Mhm.
So, and there's always plans for, like, if A happens, you do B, that type of thing. But once it's far away, who knows, you know? We think it'll work. We think
Okay.
it'll,
Would it
I tell you,
adjust?
the wonderful thing about that telescope, not to interrupt you, sir, the wonderful thing is that it's an infrared telescope.
yeah,
It looks into the invisible spectrum.
yeah,
That's what it is. It's amazing.
it is.
If I may ask once again, how far up in space is it gonna go?
940,000 miles.
How far?
940,000,
And how far up is the Hubble right now?
about 300,
All right, okay.
380.
Okay. all right.
Sir?
I was wondering if this telescope will have additional resources for
Yeah.
exploring dark matter.
I think Jim, does it?
I'm trying to come up with an answer. Because dark matter,
Yeah.
we don't know what it is. So how do you define a telescope that's looking for something you don't know what it is? So you don't know how to design the telescope. So what happens is, you look for gravity to key you in on what's going on in space. Let's say you had two interacting objects, massive objects like a galaxy. These two galaxies are colliding, right? They're interacting, they may be rotating and doing a slow dance around each other, becoming one giant galaxy, okay? By the rotational energy, you can look through the spectrographs and see how fast is it rotating, how much mass is there. Wait a minute, we're looking at the star mass. Doesn't add up. Star mass adds up to this much, and we're seeing this much mass. That's how you find dark matter. So
they'll
you
be-
can
they'll get
find
a
it
lot
by the
more
gravitational interaction of two objects, by what's missing. You add up everything you see visibly, and even infrared is telling you something's there you can't key in on. But when you add it all up, 80% is still missing. And it's just like the Milky Way is rotating at a certain speed. If the stars out in the center, going out to the edge, by the time you get to the edge, stars should be slowing down because they're far, far away from the central mass of the Milky Way galaxy, right? The hub of the galaxy, right? They don't. This is the mystery. And they're saying, in order for that to happen, there has to be some invisible cloud blanketing the entire galaxy, allowing it to compensate and have a certain amount of mass. So every one of the stars from the middle of the galaxy to the edge of the galaxy are rotating and revolving at the same time around the galactic hub. So I hope that explains.
No,
it.
that's helpful,
It's tough to explain something. Well, we're going to look for something that's invisible. We don't know what it is. We're not sure how to look for it, but we're going to go for it anyway. You know. And
But you'll get more detailed information that will
oh yes,
hopefully help.
this telescope, because of its infrared capability, punches through the intermolecular clouds out in deep space, and you can see things that would normally not be visible. We're already getting hints from Hubble. Like, what is Hubble doing now? Hubble is taking a set of images of proto-nebula that are forming exoplanets or brand new stars. It's looking at the furthest it can look into space, right at that edge that Webb is going to punch through and go well beyond. It's looking at that, and they're seeing mysteriously blobby red galaxies that don't look like galaxies, but they gotta be galaxies. What else can they be? They're baby galaxies. we can't resolve them enough to say, why do they have that shape? How many stars are in the mass of the galaxy? It's right 13.2 billion light years away, right at the observable edge. So Hubble will allow us to say 1 year's worth of viewing from the Webb is already tied up with what Hubble has already defined, saying, I can't see any further. These are mysterious objects. Scientists are really excited. They really want to know what's going on. Here, Webb, take the torch and go forward. So that's what it's going to do. So they work hand in hand. Go ahead, sorry.
Do you need to accumulate data over years of time, or can you look back and see like the rotation, or do you need to wait like 50 years to get that rotation, or can you like look back and see it the further you look back? Like, do you have to wait?
Well,
or can you look to see it move?
It's like if we landed on Earth and we went to a nursery and we took pictures. Well, people on Earth are about that tall. They yell at high-frequency pitched noises, right? They make a lot of screaming sounds, and they run around the room at 100 miles an hour. That's what Earth is all about. Oh, let's land in the Sahara. Oh, Earth is very dry. There's no water. There's nothing going on. There's no life. So what you have to do is take advantage of the fact you've got this enormous universe. And what you're trying to do is capture a baby galaxy at the beginning of time. Look at another galaxy in front of it, which is closer to us, which means it's a little younger or a little older. And look a little further down, it's a little older. So as it's coming close to our time epoch, we're seeing more and more and more galaxies that are in the shape that we're familiar with. So you can kind of look, just like you're looking at the nursery and you're looking at the Sahara and you're looking at only the oceans, you're adding it all up. Not at one object, but you're looking at multiple objects across the entire universe. And you're hoping to capture just at that precise moment of birth, just at the precise moment of the first stars forming, just at the precise moment of the second or third or fourth generations of stars. And then you can add up in evolutionary theory how galaxies form, how stars form, things like that. So it's complicated, but it's challenging and it's very interesting. And Webb makes it possible.
Once it's deployed, how long afterwards might, I know it'll take a while to digest anything, but might the public see a first look at something? Would it be
6 months?
Yeah,
6 months is the first image.
It's got at least 3 months of testing before they actually use it. It's going to unfold, become its true stuff on the way there. But once there, they have to test everything to make sure it's still working.
But might they show early on, here's a look at something never seen before? They're gonna digest it for centuries.
No, I understand that, but what people want to understand, it's like, we're launching this brand new telescope, we spent $10.5 billion, throw a switch, and it's working. And that's what everyone wants. That's what I'd love to have. But unfortunately, think about this. I am birthed on a planet called Earth. It's 75 degrees in my room. It's a water-wet world. Oh my goodness, you just hit me on my butt, hurled me into space. I am now going to 388 below zero, no moisture, icy cold, and all of a sudden, all that moisture and all that stuff you brought from a planet called Earth is leaking out. So you got to get it acclimated to what's going on in the place it's meant to park. So that's why when they're showing you the sun shields start deploying, they go a little like this. It looks like herky-jerky, like this. Like, you can't do this. You'll rip them because of the stress put on something from 75 degrees going into space, now 388 below zero. So you got to do it gradually. So they're doing this gradually over a 6-month period of time to define the focus. Now, here's focus. You ready for this? Each of those actuators behind each of those hexagonal mirrors can flex that mirror into focus within 1/10,000th the diameter of a human hair. Think about that. Does it make a difference, 388 below zero or 389? Oh yeah. So you got to make sure everything acclimates. So when it makes that final flexure, you got the ultimate image. Now, to your point, I'll bet you they will release some pre-images and saying, not quite as good as we can get, but we're getting there. Scientists are, I'm like you, I want to see it tomorrow. So hope that explains it.
Is there a question?
It's exciting.
How long does it take for the images to reach us here on Earth?
Couple seconds.
Couple seconds.
Just a matter of seconds.
Yeah. Travel has a speed line.
So it certainly is an innovative telescope. I mean, it's gonna, like you say, it's gonna change the way, it's gonna bring us to the origins of the universe.
Sure. Now, Jim had told you about, the scope has to acclimate to its temperature. If you own a personal telescope, every time you bring it out at night, the telescope has to acclimate to the temperature, and your eyes have to acclimate to the darkness. So you get about a 15-minute acclimation period when you go out. Whether or not you realize it or whether or not you use it, you get your best results after about that time. I want to make one more comment on the gold. I meant to tell you, I forgot.
Next question for you. If an adjustment has to be made at its maximum point, what's the time duration from point A to point B if NASA has to make an adjustment?
But it's almost instant, about a minute, second and a half.
Wow,
Yeah.
okay.
But the gold, as I show how they put it on, they only use that 3 grams on every octagon. They tell us that you could put 1,000 layers of that gold. It'll be as thick as a piece of paper. That's how fine it is. So it doesn't make sense to go out there to steal the gold.
Yeah,
It's
talking about
just not that much.
Yeah, a couple angstroms of gold, basically a couple atoms worth, I should say.
Where were the mirrors made again?
The mirrors were made by a company right up the road here called Materion. I used to work for them. And they have big, huge chambers where they deposit coatings on various mirrors. But this is not
But that's
a
the
glass
coating, not
mirror.
the
This
mirror
is made out of beryllium. And Materion is one of the largest providers of material across the entire globe. And they're based right out of here, out of Westford, Massachusetts. The place they mined it from is in Utah. So they put it together there, they distributed it amongst, I guess, Dino, you were saying about a dozen different facilities.
But did they form the mirror there as well as coat it?
Where did they form the mirror?
I'd be curious.
I'm trying to think, I'm gonna say
Would it be manufactured?
quantum blank.
That's amazing.
No,
Yeah.
it's on the tip of my tongue, but I can't remember.
Okay.
It's
You can
quantum
actually-
coating or something like
You can
that.
actually Google a video of it there.
Oh, you can.
Yeah, there's tons of videos on the web and the different functions
Yeah.
of it, so you can.
There's so many people involved here. It's like, who's
Right.
responsible for the mirror? Who's responsible for this? Who's responsible for that? I think all of a sudden you could rattle off 15 names and you'd be all correct. Because it's kind of like everyone is helping to get it to that point where we can launch it into space and do what we need to do.
And the other thing that makes it alive is they work in teams. You know, there's probably not one person who works on every single angle. They work in teams on certain aspects so they can be really expert at it. And you take care of it good. Any other questions that we can answer for you guys?
About the fuel,
Yeah.
they're using solar power.
Yeah.
Now, do they have like a backup, a nuclear battery or something?
No, but there's also the cryogenic fuel, Jim, right? What is the cryogenic fuel?
The cryo liquid is for the MIRI, which is the deep space spectrograph. There's the regular spectrographs. Now get this, are you ready for this? I had a professional astrophysicist explain this to me. He says, take a look at this picture in infrared light. On the left was a meerkat. On the right was an alligator. Then he takes it in visual so you can see the difference between two animals. Then all of a sudden he turns on the infrared camera. And you can see these meerkats are glowing, yet white hot, right? Because they're warm-blooded mammals. You can hardly see the outline of the alligator. He says, MIRI will look for the alligators of the universe. And I thought that was perfect, because there are objects forming that are just at the point of starting, things going on with stars forming, but not like 100 billion stars, maybe a couple tens of thousands of stars. Those are going to be glowing alligators. And you need something even more sensitive. And as Dino pointed out, they call it a cryoliquid. So if you think 388 below zero is cold, drop it into liquid helium, which is on board, and that's the limiting essence of that particular device. When you run out of the cryoliquid, that's it. But it will drop it to almost absolute zero, which is minus 454 below zero. And talk about accuracy. That's how, it's definitely got, that sun shield, everything on the other side of the sun shield, the sun, the reflection of the light off the earth, and even the moonlight is all shielded And that's where all the antennas are, that's where all the hot button items like the rocket engines to kind of steer it and put it into an adjusted orbit is located. So that's important to understand that. But I think about it, 388, I'm freezing. 454 blows my mind.
Marie, you had a question?
Oh, I just wanted to go back to, it said that Webb would be launched on December 12th of this year? Okay, so exactly a month from now.
It's December 18th at 7:20 in the morning.
Okay,
Well,
is there,
right now.
is there gonna be like a, I don't know, a big thing? Like
Well, it'll be on NASA TV.
a celebration?
I'm sure it'll be on the news.
NASA TV and about 50 other places on the
Yeah,
internet. Lisa will have it.
Yeah, if you go to
broadcast
NASA,
overseas.
nasatv.gov,
Mhm.
I'm sure it'll be there.
Will
Sure.
they have a
Okay,
live
great.
feed as well, so you can
Probably,
see
yeah.
the
Yes.
opening
Yeah,
process?
they usually do, yeah.
Well, absolutely. I didn't look that deep. They'll have a live feed telling you what is actually happening. Now, I don't know if it'll be live, meaning you'll
Like
see
a camera?
real images of the spacecraft separation and things like that, because we're getting spoiled with SpaceX. They got all these high definition
Yeah.
images of every part of the rocket, including reigniting the engine and landing. It's just amazing. I don't know how much they've invested in that for the Webb.
Check space.com, they may have
Yeah.
they may have it.
Space.com is a good place, spaceweather.com is just what's up in the night sky, talk about this. But like Dino said, NASA will have it broadcast, definitely. And the Europeans are definitely going to be broadcasting it. So there's going to be a lot of, like I said, there's a number of individuals have been with this whole program for 30 years. So think about a 30-year work history. I'm ready to retire, right? And they're still waiting for something to happen because of what they invested in. And I'll tell you, the 8.5 minutes from that rocket ignition and the boosters kicking in to getting into space and it's heading toward L2, you're going to see a lot of, with their fingernails just being bitten down to the bone. They're just nervous, and I can appreciate that.
There's no backup mirror or anything,
No,
that's it.
you trust. You researched it. You put it on a shake table. You put it on a pump down chamber, a huge vacuum chamber where you can test it at those temperatures. So we've tested it at those temperatures multiple times, and they open and close perfectly. But one thing you can't test for here on Earth is gravity. So you have like cables that kind of take away 3/4 or 90% of the weight of the sun shield. So it kind of allows it to stretch out as if it was in microgravity. You test it as much as you can. So they're not just hoping, they tested it. But until it's in space, that's the final orbiter.
Do you still have time to set up outside?
Yes, I'm going to take a little bit of a break. I'll grab my stuff and go right outside.
So if you want to see.
Dino can answer.
He set it up, showing the scope, he's setting up outside, it's a very nice scope. And if you want to see the Jupiter's right up above us.
Jupiter and Saturn and the moon.
In the moon. The moon is surprisingly a very nice object to watch, because the way you see in the craters and the shadows. And Jupiter has the 4 Galilean moons in plain view right now. Hopefully the cloud cover hasn't come on. So Jim just need about 5 minutes to pack up his stuff. And thank you all very much for coming.
Thank you. Very good presentation, nice job.
Thanks, Dick, I'm glad you joined us.
Bill, they're still predicting rain? Because I heard that the weather was going to clear after 1, so you'll be able to see the eclipse. Because I thought it was going to rain all the way through morning, and we missed the eclipse here. But my friend called me, and he said, "What are you talking about?" So something must have changed. This is terrible.
Oh, man.
This is why you set up a
Here it is, here it is,
program.
here it is.
Oh, there we go.
Oh, here we go.
Please, please.
Get in there. Get in there.
You might get another
Nope.
little. Give it a second.
Give it a second. It's coming out.
Hold on.
There's one more little
Go for it.
little window
Okay,
coming
we got
up.
to scream and yell and urge the cloud.
There it is.
Oh,
Boy,
there you
it's
go.
fast though.
Wow.
Clouds are moving.
Isn't it amazing? The clouds
Look at all this.
distort your view.
Yeah.
You feel like you're you're doing 100 miles an hour
As it sweeps by.
This,
and let the library know that we did a good job, and
Yeah.
also
You did an
Sure.
amazing job.
look into the library telescope. It's a lot of fun to take home.
Oh, really?
I'm going to make sure they have a video, because we produced a video that tells you how to use and how to
Oh,
set it
wow.
up and how to put it back safely.
Oh,
So
nice.
people are a little nervous about flying
Yeah.
the telescope,
Wow.
but we'll make sure they have a copy of the video.
Yeah, I'm building a radio telescope with
Oh, you got to come down our place.
Yeah.
We're talking to a couple members for amateur radio above.
Yeah.
And they're advising us on building a radio antenna to maybe get the signals from Jupiter and maybe the signals
Wow.
from the sun, or
Yeah.
maybe even from the center of the Milky Way.
I have this like simple build here.
Ah, okay, cool.
Yeah, I got a little
No,
antenna.
something simple.
Yeah, LNA.
Yeah, you don't need anything elaborate.
Yeah.